Okay. Yeah. So I'm just going to be talking about quantum squeezing in Dicke materials. This is a 2D material session, but my talk has nothing to do with 2D materials, so apologies if that was the expectation. But let me start by explaining what are these Dicke materials. So the idea is that these materials are materials which can be avenues to realize, as their name suggests, some Dicke models. So I'll just go through the Dicke model quickly. So the Dicke model is a very popular paradigmatic model for light matter interaction, has been studied for many, many years. It has it has a very simple form. So we have some independent atomic spins, which have some excitation frequency omega naught in some direction. We have a photonic mode with some excitation frequency omega. And then finally, there's some light matter coupling term, which couples this photon to these spins. This Dicke model has some very interesting features. It can be used for interesting quantum information stuff. It exhibits quantum chaos. And more interestingly, it has this superradiant phase transition. Now, this superradiant phase transition has some controversies because of these no-go theorems. So it turns out that if this Dicke model really is like electromagnetic photons having some electric dipole coupling to the atomic spins, then there are some no-go theorems that say that this phase transition to the superradiant phase does not happen in equilibrium. Its non-equilibrium analogs have been observed in cold atoms and trapped ions, but there's controversy about its equilibrium realization in like a real system. So the key idea of this Dicke material is essentially that if we can replace this photon mode with a different bosonic mode, for example, in this case, it would be magnons, then essentially this no-go theorem does not directly apply. And then that gives us hope that maybe in a solid-state system, one can realize these Dicke model superradiant phase transitions in equilibrium. So that's the idea. So the Dicke material, I'll just sketch out sort of a bare bone structure of what it means. So imagine there are two species of atoms, red and blue, and they both are magnetically ordered in some way. And so the idea is that let's imagine the blue atoms have some spin exchange energy scale JB. The red atoms have some internal spin exchange energy scale JR. And then the blue and red atoms also couple, their spins are coupled with some scale GRB. And then each of them can have their own excitation frequencies along some axis, omega B and omega R. So the first feature we need to make this a Dicke material, to have some sort of a Dicke model in it, is that let's imagine that this spin exchange within the blue atoms, J of B, is the largest energy scale in the problem. If that is true, then one can imagine that the excitations, the spin excitations in these blue atoms can be very well described by magnons. So that gives us this bosonic field, which we need for a Dicke model. So in the Dicke Hamiltonian, that takes care of this photonic or this bosonic term. Next, what we want is that this spin exchange term within the red atoms, just JR, is very, very small compared to its excitation frequencies, which essentially means that these red atoms act as paramagnetic independent spins. And that takes care into this account of this second term, which is just some individual atomic spins in this Dicke model. And finally, because these blue and red atoms are coupled together with some term GRB, that would supply this third term, which is this light matter coupling term, or a coupling term between the magnons here and these red spins. So that's the essential idea of this Dicke model in this Dicke material. The second feature we would also need is we would need some sort of a strong coupling of these two species of spins. And that's because if you want to see some superradiant phase transition, this coupling better be not to be too weak. And the third feature is that it will be nice if some of these parameters are tunable by some external fields in an experiment so that one can drive like some sort of a normal to superradiant phase transition. So recently, earlier this year, there was a paper from Professor Jun Kono's group where they observed that actually erbium orthoferrite is an example of such a Dicke material. And the idea is analogous, that in this material, there are these two kind of magnetically ordered spins, iron and erbium. The iron ones have strong spin exchange coupling among them, so they supply the magnons, which are the bosonic modes. And then these erbium atoms acted as independent spins, so those are the atoms in this Dicke model. They predicted that both temperature and magnetic field can drive a phase transition between a normal and a superradiant phase in this erbium orthoferrite material. And the way to diagnose this, a nice way to diagnose this, is by looking at its polariton spectrum. So here, the idea is that this Dicke model can be diagonalized in terms of two polaritons. omega plus and omega minus. So here, what I've shown here is motivated from this experiment where in this effective Dicke model that this material realizes, this coupling between the bosonic and the spins G is fixed to be some number, 0.1 omega. The x-axis is tuning the ratio between these two excitation frequencies, omega and omega naught. And these two polariton frequencies are just these two lines. And the nice thing is that as one tunes between the superradiant and the normal phase transition, the lower polariton mode becomes very soft. So there's a mode softening. And at the same time, for the upper polariton mode, there appears to be a kink. So this would be the signature for such a phase, for this phase transition within a Dicke-like model. And the nice thing in this experiment or in this material is that this ratio omega naught over omega can be tuned by magnetic field, so one can drive this transition. And they saw exactly that. So in this experiment, in this paper, they saw that at some magnetic field, they noticed that this lower polariton mode showed a lot of softening, and at the same time, the upper polariton mode showed this kink. So that was spectroscopic evidence that this material is nicely described by this like Dicke kind of model, and there's this normal to superradiant phase transition happening in this magnonic way. Since we have that, since we have this feature, then a nice question we can ask is that if we have these Dicke materials which implement these Dicke models, is there a way to see some other nice macroscopic quantum effects? And so what I'm going to be talking about is a potential to maybe observe quantum squeezing in these materials. So let me briefly recap what I mean by quantum squeezing here. So quantum squeeze states, they are useful states for quantum metrology. They have some utility. And also, as we heard in the earlier talk about quantum Fisher information, quantum squeezing is also a witness to multipartite entanglement. So observing this kind of a squeezing is also tells you that your quantum state is entangled or there's some many-body entangled in your material. So the simple picture of squeezing here is that imagine we have two observables, Q1 and Q2, and they don't commute with each other. Then we know that they obey some sort of a generalized uncertainty principle. So there's this stand-up quantum limit, which essentially says that the uncertainty of measurement in both these observables, Q1 and Q2, their product is bounded by their commutator. And this circle shows that there's equal uncertainty in measuring both of them, which is limited by this uncertainty principle. But one can sort of circumvent that in this sort of clever way, where if you prepare a quantum squeeze state, what you can do is that you can deform this uncertainty circle into actually an ellipse. And what happens is that you can then imagine that the uncertainty of measuring this Q2 observable is lower, but it's also at the expense of increasing the uncertainty in measuring the other observable, the conjugate one, Q1. But this is the idea of quantum squeeze states, where for one observable, you can surpass the standard quantum limit. So some example is like spin squeezing, where we know that like the spin operators Sx and Sy don't commute. So you have a similar, one can do the similar deformation to get us quantum squeezing. And also in bosonic modes, we have this position and momentum modes which don't commute. So again, a similar squeezing picture applies for that as well. And it's going to apply here too. So here, now I'm going to show that in Dicke model, there's also quantum squeezing, which actually is best near the superradiant phase transition. And one nice way to see that is through its polariton spectrum. So as I said, this Dicke model can be diagonalized in terms of two polariton modes, omega plus and omega minus. So let's focus on this lower polariton mode. So this lower polariton mode, I can imagine I can treat it as just a normal oscillator mode. So I can write it down as some sort of a harmonic oscillator with two conjugate variables, Q1 and P1. It can also be written as a ladder operator, C1, C1 dagger with some excitation frequency omega minus. Once I have that, I can redefine these conjugate operators Q1 and P1 in terms of my ladder operators. And then it's very clear that these are conjugate, they don't commute. So there's some sort of possibility of squeezing happening there because they obey this uncertainty principle, right? So in the ground state, one can calculate the variance of these operators, right? So now if we just simply calculate the variance of this operator P1 in the ground state, it turns out it's directly proportional to omega minus. And the nice thing is that exactly at the phase transition, this mode softens, this omega minus goes to 0, which essentially tells me that the variance of this operator P1 is going to 0. So it's getting like perfectly squeezed. And of course, that happens at the expense of the other. So the variance of this, its conjugate operator Q1, actually inversely proportional to omega minus. So as this mode softens, its variance actually blows up. So it's perfectly anti-squeezed, in fact, which is expected. And now we can see what is the squeezed quadrature. So for this Dicke model, it turns out this operator P1, which is this most squeezed operator, is actually a two-mode operator. So it has both this bosonic mode, this A dagger minus A. It also has the spin mode, so the collective spin operator in the y direction Sy. And both of these are weighted by some factors, which is cosine gamma and sine gamma. And this angle gamma is actually controlled by the parameters of the Dicke model. So which is nice because if one can tune some of these parameters of the Dicke model, for example, in the experiment I showed earlier, one can tune the relative weight of these 2 degrees of freedom in this squeezed quadrature. So depending on this value of gamma, one can make squeezing to be mostly in the spins or mostly in the bosonic mode, or equally distributed between both. All of these are possible. The next thing which I wanted to see is that, okay, if the squeezing is expected to be there near the phase transition, and if one wants to see if it could be ever realized in a material, then it better be like robust to some sort of temperature disorder, things like that. So the first thing I look at is what happens to this squeezing at finite temperature. So this is a calculation where essentially the important detail here is that I plot this quantity C, which is whenever it's less than 1, that implies squeezing. So this is a contour plot where on the x-axis, I measure how far I'm away from the critical point where the superradiant phase transition happens. And on the y-axis is just temperature in the units of this excitation frequency omega of the bosonic mode. And the nice thing here is that there's this large region where it seems that the squeezing parameter is less than 1. So there's some squeezing. Of course, it gets better as one is closer to the critical point and to 0 temperature. But it's nice that it survives up to a temperature on the order of omega. It also is squeezing is there even if you move away from the critical point a little bit. So that was kind of nice to see its robustness. Finally, I also looked at squeezing as a function of some sort of dilute disorder in my Dicke model. And the key message is that it does survive it. So what I did essentially is I looked at the Dicke model for like n spins, which is just the normal nice Dicke model we have with all its symmetries. And then imagine I add some disordered spins. So there are some m number of spins which have some disordered excitation frequencies, some disordered couplings to this bosonic mode. And if I look at the limit of dilute disorder, where I consider that the number of disordered spins is much less than my non-disordered spins, so this is like a dilute disorder limit, it turns out that this squeezing ratio only gets some additive corrections. And the correction is actually exactly proportional to the fraction of disordered spins in my system. So that was nice to see that perturbatively squeezing is stable to disorder, especially if the fraction of disorder spins is low, then it's nice, and this is realizable. Of course, this calculation was in the perturbative limit where this G prime over omega prime, these disorder parameters small. Just to check, I also did some small system numerics to go away from this perturbative limit. But of course, these systems are small. This is not like a thermodynamic limit kind of calculation. But it's nice to see that the generic trend holds, that the squeezing ratio just sort of directly depends on the fraction of disordered spins. And it's happening even in this non-perturbative limit. So that was nice that it does survive some amount of disorder. So finally, I'd just like to summarize. We saw that there are these Dicke materials which realize Dicke models where the bosonic mode is not a photon, but it's actually a magnon. It's a nice avenue to see Dicke model physics. One example being erbium orthoferrite, which earlier this year was shown that there was some evidence that there's Dicke model-like physics happening. And finally, near this superradiant phase transition in a Dicke model, there's expected to be this quantum squeezing effect, and it appears to be robust to some finite temperature and finite amount of disorder. Yeah, with that, I'd like to thank you all for listening, and I'm happy to take any questions. Thanks.
Any questions? Thanks for the presentation. I'm wondering, so in this, so near the critical point, the operator being squeezed seems to be a combination of both the boson and the spin operators. So am I expecting also you can do the measurement for only spin operators more accurately near that point, or you have to measure the combination of that two operators, make it accurate?
Yeah, so yeah, if you measure one of the single ones, which is like maybe just the bosonic part or the spin part, then the win you get is this weighting factor, this cosine or sine gamma. So yeah, so you get this one is perfect, you get the zero variance, but if you measure one of these, you get like a cosine squared or a sine squared. And of course, as you weight them to one towards the other, it turns into one of these.
So even if I have a perfectly squeezed limit, it's not really accurate for measuring one of the operator. Right?
Yeah.
Thank you.
So how do we actually determine the change coupling between the erbium and iron?
So that detail, I think it's I think you mean in the experiment, right?
Okay.
I'm not very familiar with the details of the experiment, but I think fit to their data or something, but yeah, not that familiar.
Any other questions? If not, let's thank the speaker again.